Okay, so now we're going to talk about the most common measures of variability and the most basic measures of variability and what they mean and how they are derived and why we use them, why we do them the way we do. We've talked about our three measures of central tendency. We had one video on just the mean because I think it's important enough to merit its own video, and then we had another video on the median and mode as alternatives to the mean because as good as the mean is, sometimes it's not appropriate in some data, and so sometimes you need to use another measure of central tendency. But now we've got those three good measures of central tendency. Now we need to recognize the fact that that central tendency is by itself not a perfect measure of a distribution. Of course, no measure of a distribution is perfect. Only the distribution itself is a perfect representation of itself. But now we need to really wrestle with the fact that not everyone is the same. Not all of the data have the same value. So the data vary. To vary just means to be different. And we know there is some error with respect to the mean, although there is no net error, right? Nevertheless, almost all of the observations are not exactly equal to the mean, and some are a little above the mean, some are a little below the mean. It would be good to have a description of how much of this error there is in any given distribution. Another way to say this is it would be good to have a description of how spread out the distribution is around the mean. So yet another way of saying it, we're looking for values that will tell us the difference between that skinny distribution there on the left and that flattened distribution there on the right. In the first distribution, there's very little variability. Everything is close to the mean. In the second one, my laser pointer did not activate. There we go. In the second one over here on the right, there's a lot of variability, a lot of dispersion around the mean, a lot of observations that are very small, and a lot of observations that are very large. Here, there's almost no observations that are very small, almost none that are very large. They're all really tightly packed in around the mean. So we want a number that will tell us whether our distribution looks like this or more like this. So we want a way to summarize how much distance there is around the mean. So why not just take the distances of each datum from the mean and add them all together? Why not just do that? Do you guys remember from the mean? What happens when we do that? Well, remember that the whole reason we like the mean so much is that the deviations about the mean, in other words, the errors, always add up to exactly 0. There's always 0 net error with respect to the mean. So we can't just take all the distances from each datum to the mean, which is what these errors are. Remember, they're also called deviations about the mean, and add them up because they'll always add up to the same number, and that's not very useful in telling us whether we're looking at a that really tightly packed distribution or that more spread out distribution. So what else can we do? Well, one possibility would be to take the absolute value of those deviations and then add those up. It turns out that when we do that in a sample, it becomes difficult to develop estimators of the corresponding population parameters because just taking the net deviation around the mean, or I'm sorry, not the net deviation, taking up the net absolute deviation about the mean depends on sample size, right? So that's going to make it very difficult to come up with unbiased estimators for our population parameters corresponding to adding up all the distances around the mean. So what else could we do to get rid of the negative values? Well, you're probably thinking what I'm thinking. The square of a negative number is a positive number. So we could get rid of all of the negatives in the distribution of deviations about the mean by squaring them. And that is exactly what statisticians do. So the square of a negative is positive, the square of a positive is also positive, so we could just square all the deviations and then add those up. And that will give us a measure of how much deviation about the mean there is. So what is the first squared deviation about the mean in these data? So what am I asking here? Well, we're talking about this number, right? That's the first deviation about the mean. What is the square of that deviation? You can probably do that one in your head. You don't even need a calculator. So that first deviation, of course, is 4. Now, you might want to stop the video here and see if you can do the rest of the deviations. Of course, there's a lot of them. Do a couple. Just make sure you understand the concept. All right, did you stop the video? You didn't stop the video. Well, I'm going to go on anyway. There are the rest of the deviations around the squared deviations around the mean. So each number squared, and now we have our squared deviations. And now, for just a second, forget about what these numbers are and where they came from. One way that I can summarize all these numbers is to add them all up to find out how much of this stuff I have. The stuff in this case is squared deviation about the mean. I can just add it all up. So yeah, how might we just derive a single number to describe this? How would we figure out how much money we had? Just add them all up. And so that's exactly what we do. And that statistic is called the sums of squares. Technically, its full name is the sum of the squared deviations about the mean. And so we're just going to take all these numbers here and add them up right here. Same way we did adding up the net deviations here. And I'm presenting another equation now. So notice how if you lay out your problems this way, it becomes fairly easy to start reading these equations. So we had x sub I, that's x sub I right there, minus the mean. And remember, the mean of these data was 4. We calculated that in the average video that we did. And so here was the deviation about the mean. We squared that, so we're just taking x sub I minus x bar, that deviation about the mean, and putting it in parentheses and squaring it, and that is what this number is. And that's pretty simple to understand, right? So now if you look at this equation, do you remember what that symbol means? That just means add them all up. So we're going to add up all of the squared deviations about the mean to get our sums of squares, or sum of squares. It should probably grammatically be sum of squares, but I think most people do say sums of squares. Interesting. Maybe somebody will correct me in the comments. All right, and there's our sum of squares. If you add them all up, they add up to 40 in this case. Okay, well now we have a number, a single number, that describes for this distribution of extraversion how much deviation about the mean we've got. Now it's got a couple of problems with it. That number has a couple of issues. For one, it depends on the sample size. If I were to add one more person to this sample, I would get a bigger sums of squares. If I were to take one away, I would get a smaller sums of squares. So the sum of squared deviations about the mean is dependent on sample size. It's also in squared units. It's no longer in these units of extraversion that we measured. It's in the square of that unit, whatever that is. I don't know what squared units of extraversion would even mean. So we're going to take care of both of those problems. So what if I add more observations to my sample? We've kind of gone over that. Sums of squares will increase, right? How can I remove this dependence on sample size? So let's tackle the sample size problem first. I want to deal with the fact that this number here, this 40, depends on the fact that I have 16 people in this sample. If I had 17, it would be a little different. If I had 15, it would be a little different. If I had 100, it would be a lot different. And I don't want to think about the sample size when I'm thinking about this number. I don't want to have to judge this number relative to a sample size. So I just want to get rid of the sample size altogether. How can I do that? Well, forget for a moment again where these numbers came from, and just think about how you might go about describing this distribution. Remember, what we want to describe about this distribution is how much of it there is. How would you do that? Well, how did we do it here for these numbers? Well, for these numbers, we calculated the mean, right? Why couldn't we just do the same thing here? Just calculate the mean deviation, squared deviation about the mean. Yeah, take the mean. And that's exactly what we do. So we symbolize it with the sigma squared. If you remember the video on statistical symbols, this statistic has a name. We call this statistic the variance. And it's just the sums of squares, that's this guy right here, divided by the sample size, which is exactly the same thing we do when we calculate the arithmetic mean of extraversion, right? We just added up all these numbers and divided by the sample size, and that gave us the mean. So the variance is the same thing as the mean squared deviation about the mean. That's a mouthful, huh? The mean of the squared deviation about the mean, also called the variance. All right. Now, that formula, that very simple formula, is actually the formula for the population variance, and that symbol, the sigma squared, is the symbol for population variance most of the time. If we're talking about a sample, of course that's all this was, right? The example was a sample. Then the symbol we use is little s, lowercase s squared, for the sample variance. This is the sample variance, and there's a slightly different way we have to calculate it, which is the n, we have to take 1 away from it, n minus 1. You don't need to really worry about the reason. I'll tell you what the reason is, but you don't need to worry about it unless you're pursuing statistics as a profession. The reason is that the statistic, let's go back one. This calculation, when done on sample data, tends to underestimate this statistic done on population data. And taking 1 away from the n actually corrects that, so that this calculation is an unbiased, this calculation carried out on a sample, on sample data, is an unbiased estimator of this calculation carried out on population data. Now, if that doesn't make any sense to you, don't worry about it. Just know that when you have a sample, you have to use this formula. You have to add up the sums of squares, and then instead of just dividing by n to take the average, you divide by n minus 1 to take the average, and that gives you your sample variance. Now, the sample variance is nice. It's very commonly used. Now, whatever number I get for sample variance, let's get the number for sample variance. Yeah, okay. So there's our number for sample variance. And that number, 2.6667, of course, it's an estimate. It will change slightly if I change the sample size. It'll change slightly if I increase the sample or decrease the sample, but it won't systematically go up or down. In other words, it will change, but it will only change randomly, and it will only change because of measurement error. It won't change systematically because the sample's getting bigger. So in other words, if I add 100 observations to this sample, the number I get for variance will still be very close to 2.6667. And if I take away, say, 5 of these observations, the number I get for variance should still be pretty close to 2.6667. So this number, I no longer have to think about my sample size to think about this number and whether this is a big number or a little number, whether this means I'm looking at a tight distribution or a very distributed distribution. Sample size is just no longer an issue because of this division right here by n minus 1. But as good as this number is, it still has one inconvenience, which is that this number is still in the square of whatever unit I measured in. So if I measured in extroversion on a scale from 1 to 7, let's say, this is in the square of those units. So this is in units from 1 to 49. And I don't even know what that means. What do units of squared deviation mean? I have no idea. I just want to think in terms of my simple scale from 1 to 7 of extroversion. I don't want to think in terms of a squared unit. So I want to do one more thing to this to come up with an even more convenient number. Can you guess what that is? I'll bet you can. That's right. I want to take the square root of it. So just to give you another example, if we measured length, if these numbers meant length instead of extroversion, my variance is in units of area, right? Length squared is area. I don't want to think about that. I want to get a number that is in the same units that I measured in, so I can do that by just taking the square root of the variance. And when I take the square root of the variance, I get another statistic called the standard deviation. All right, so let's calculate the standard deviation for these data. You might, stop the video here and calculate it yourself on a hand calculator or whatever. All right, and there it is. So the standard deviation is 1.633, and this is in the units, same units as this measurement scale right here. So the standard deviation is in the same units. It does not depend on sample size, and so this right here tells me whether I've got a tightly packed distribution or a widely distributed distribution. The only thing I have to think about in interpreting this number as meaning the narrow distribution or the wide distribution is the range of the scale that I'm using. So this scale went from 1 to 7. The standard deviation is 1.6. So that's a pretty tightly packed distribution. That distribution does not have just a whole lot of spread in it. If standard deviation had been, say, 6, and a scale that only went from 1 to 7, that would be a huge distribution. That would be a huge variability in the distribution. Okay, what else do I want to say about this? I think we're just about done. Oh yeah, so let's summarize. So when we want to describe how much of something there is, something that we've measured, we can use a measure of central tendency, and the most popular one is the mean. We can use alternatives, the median and the mode, sometimes. When we want to describe how variable the distribution of numbers is around the mean or around the central tendency, we can use measures of dispersion, also called measures of spread, also called measures of variability. And the three that we covered here were the sum of squares, the variance, and the standard deviation. Standard deviation is usually the preferred one because it doesn't depend on sample size, and it is in the units of the measuring scale that you originally used to measure your variable, whatever that was. So people like standard deviation a lot. Now there's a lot of other measures of variability. I'll talk about those in other videos later, but these are the three that you've really got to know, especially to get started in statistics. Once you've been going in statistics for a while, you can start looking at standard error of the estimate and standard error of the mean, a bunch of other measures of variability. You do know actually already one other measure of variability, probably, right? The range, which is just the maxima minus the minima, the biggest datum minus the smallest datum. That's the range. And that's another really quick and easy measure of variability, but it's kind of crude. The standard deviation has a lot more information in it, and so people usually prefer the standard deviation. All right, I think this video is long enough. Let's cut it there.